What I'm going to be discussing here today is a workflow for well performance analysis in the Bakken. And so we're starting with an example, and you can see we've got oil production rates, gas production rates, water, and some pressures, and I'll talk a little bit more about this in a minute. We've got a production history that spans almost 4 years. I'm going to just add on here gas-oil ratio and actually show the gas-oil ratio instead of the gas rate. And that gives us a little bit more detailed picture of what's going on with the relative fluid ratios. So what you're looking at here, we've got our oil production rates. The well comes on stream at over 1,000 barrels per day, 1,100 barrels per day. We've got some decline. We've got a little bit of a shut-in period here, and then continues to go from there. Oil data will tend to have some noise. This is a pretty normal-looking production history in the Bakken. What we also see is GORs that are in the vicinity of about 500 barrels per million. There is a little bit of an increase in the GOR late in life, but even towards the end it's still under 1,000 barrels per million. What that's going to be an indication of is that it's a highly undersaturated oil. We're still very much, for the majority of the reservoir, in the undersaturated range. There may be gas being liberated near the sand face, but for the most part we're single-phase oil. Let's take a look at the water rates. We've got some water production, again very noisy. Water production rates are significantly lower than the oil production rates. That's good. That shows that we don't really have to deal with formation water flow in the reservoir. We can think of this as being primarily a single-phase oil case. Now let's take a look at the pressures. Understanding the flowing pressure behavior in a well like this is critical. And it's not an easy task either, because as you can see, if we look down here, we have at the beginning casing production, and we'll talk about this a little bit more when we get to the wellbore section. We've got casing flow, and then tubing is installed here. So these are the actual measured pressures while the well is flowing. And the well flows up until approximately April of 2009, and then it goes into pumping. So the well is now an artificial lift from this point going forward. As you can see, the calculated bottom hole pressures show that we have are shown here in black. These are calculated from a pressure loss correlation, multi-phase pressure loss correlation, and then from the point where it's artificial lift going forward, we really have limited data on what the bottom hole flowing pressure is. That's something that we have to deal with in plays like the Bakken a lot. We don't have a permanent bottom hole gauge to measure pressures, and we don't have reliable surface information that can, or liquid level information that can provide us detailed information on bottom holes. So really we only have one flowing pressure or flowing gradient that was run in November of 2009, and then we've got some information near the end of the data about bottom hole flowing pressure being quite low, around 500 psi. So there's not a whole lot of detail here, but this is fairly typical. So let's go ahead and go into the analysis. I'm going to go right into the workflow. And so let's start with some initialization. I think it's really important to understand the fluid properties in a case like this. We're looking at initial pressure of about 6,500 psi. And if we take a look at the oil properties, we've got a fairly low bubble point of 2,000 psi. That gives us a solution gas-oil ratio of about close to 500 standard cubic feet per barrel. Again, that's consistent with what we see in the field data. So that's properly calibrated. If we can, we want to be able to get a PVT analysis where we can confirm this. In the absence of a full PVT analysis, we can get pretty close just by understanding and looking at the field data and seeing what the well produces at the wellhead for produced gas. The other thing I want to take a look at here are the rock properties. We have a net pay of 50 feet. That's pretty normal in the Bakken. It's a thin formation. Typically the petrophysicists have fairly good confidence in the net pay thickness of the middle Bakken. We also have oil saturation of about 75%, porosity of about 7%. Let's move on and take a look at the wellbore. As I mentioned before, we have a situation here where the initial configuration is tubingless. So we've got flow up the casing. Starting very early in the production life, tubing is installed to get a lower area to flow. Tubing is installed, and then we carry on from there. About a year after the tubing is installed, that's when the well goes into artificial lift, and that's where the pressure information becomes lacking for the most part. We don't have a whole lot of information to go from after that. Let's jump right into the analysis now. So to do a workflow that's consistent with the Bakken, fairly straightforward, what we want to do first is we want to take a look at the standard unconventional module. So I'm going to choose oil as my fluid. I'm going to go to superposition time and pick the deterministic option. And this will give us our standard 4-plot square root of time plot here, done using superposition time. We always use material balance time as our time function. We found that works the best in the vast majority of cases that we have. So that's our square root of time plot. This is our flowing material balance plot, and then our type curve on the bottom left. What we're going to be using this module for is two different things. One is to help characterize in a qualitative way what the flow regimes are that we see in the reservoir. And so we're going to do that sort of interpretation, qualitative interpretation. Number two, we're going to try and extract some reservoir characteristics by making some assumptions about the geometry of the system. We'll have some bulk reservoir characteristics, and we'll try and come up with estimates of fracture lengths, permeability, fracture conductivity, and possibly minimum drainage volume in this well. Let's start with the superposition plot. We're going to scale it to get a better look at what's going on. I'm going to make some adjustments to this line. By default, the program is going to do a best fit of the first section of data. I think I can do a little bit of a better job. I'm going to move that down to the origin, maybe flatten that out a little bit there. What I think is happening here, and I see this in the Bakken quite commonly, is we have a departure from linear flow very early in the life, but it's a very subtle and slow departure, so there's a significant amount of pressure support. So I'm going to go ahead and move that green line all the way back. So it's very close to the beginning. Our early linear flow is actually very short-lived in a well like this, and it starts to depart from the straight line behavior very early in the life of the well. As you can see on the type curve down below, our red curve doesn't match the data very well at all. That's why, or the reason behind that is we haven't yet adjusted the post-linear flow B value. So I'm going to go ahead and do that now. Let's try putting 1 in there. And 1 would be our solution for boundary-dominated flow. As we can see, the data is still above that solution. The brown line that's there is linear flow. This would be boundary-dominated flow. Our true data seems to have a trajectory that goes in the middle of those two. So I'm going to suggest maybe it would be something like 1.4, maybe 1.3, 1.4. That seems to match the data quite well. So we have a sort of an idea of what flow regimes we might be seeing here. Very early linear flow, transitioning very quickly into something that's consistent with pressure support that you might get from very tight rock feeding into a stimulated reservoir volume. And so that's what we're looking at here. Let's take a look at the flowing material balance. As you can see at the moment, there's no line on the flowing material balance. I'm going to go ahead and make a selection there, get that line to come back. That should be consistent with the dotted green line there. As you can see, there's a lot of data that supersedes the trajectory of that line. That indicates that we've got a very early contacted or stimulated volume that's seen here, but the well is still in transition, significant transition. We've got some clear pressure support beyond the SRV that we see by that first line. So that's our diagnostic interpretation. Now let's enter in some information. Our well length in this case is 10,000 feet. So I'm going to put that in. We have 35 fracture stages in this well, and what we will immediately get as a result of everything being lined up is an estimate of permeability and an estimate of fracture length. So that comes out of the interpretation. Let's move on now. I think we've gotten what we can from here. I'm going to right click on this one and rename it, and we'll call this flow regime identification, and move forward from there. Next step is we're going to take a look at the flowing material balance. This will give us an idea or an estimate of what the total contacted oil in place is. So we've done our flow regime identification. Now what we want to get is an idea of our contacted oil in place. This one's pretty easy. We just take a late time to trajectory on the flowing material balance, and where that line extrapolates to the x-axis or the intercept, we get our estimate of oil in place. That's coming up with about 4,400 or 4.4 million barrels in place. Again, that's probably a minimum. This hasn't necessarily seen all the boundaries yet. It may continue to flatten out. The area in this case is close to just shy of 300 acres. In this particular development, we have 2 wells per section in this part of the Bakken. And so this well really only has access to about 320 acres. So we're fairly close to the volumetric limit of what can be drained for this drilling development. So let's move on from there. We're armed with some information now. So the next step is to create an analytical model for this case. We'll go into Analytical Model, Oil, Horizontal Multifrac, and we're going to use our Enhanced Frac Region model for this one. We're going to start by seeding the model input parameters with our reservoir inputs and then the results from our flow regime ID. For XI, we're going to use the maximum value, which is equal to the well spacing. And this just gets us started. What I want to look at first of all is just our history match. And as you can see, our simulated production or pressure response matches the data at the beginning, but quickly diverges from the actual pressure response in the data. The reason for this is if we go back and look at the flow regime ID analysis, we can see that all that we're doing here, this is a simple yet rigorous model, all that we're doing is modeling the SRV. We're not modeling any contribution on the outside. And it's very clear from this interpretation that there is pressure support. There is matrix rock that is adding significant production volumes on the outside of this SRV. So if we go back to our analytical model, it becomes clear why this picture looks the way it does. I need to add more reservoir volume, more drainage volume to this interpretation. So let's minimize this. The easy way to do that is to go up to the schematic. We can increase the reservoir width by doing that. And very quickly we can see our pressure response is now much more consistent with the flowing pressures that we see in the history. Now what do we want to use for the reservoir width? Our starting estimate is going to be based on our flowing material balance. So we extrapolate that, as we saw before, that's close to about 4.5 million barrels of oil in place. I'm going to enter, to get that one started, 1220, and that gives us pretty close to 4.5 million barrels in place. So that's going to match with our flowing material balance interpretation. If we now look at our history match, we can see it's fairly close to the actual data. The simulated data is above. We're now going to try and match that simulated data. As we know, for a model, we need to improve that match. Our starting interpretation is always going to be a little bit off. We need to improve that match to the actual data. Before we get that process started, I want to make sure that I'm using only data points that should be included in the weighting. As we can see from the pressure history data, not all of these points should have equal weighting. The well is flowing at the beginning. We clearly have some productivity issues through the middle region here, and then the well goes on pump after this. So where the pressures are smooth, these are all just interpolated values. We don't want to put weighting on these. There is one point here where we do have a liquid level, so we're going to use that. And then there's a point at the end where we want to make sure we're matching to for the production forecast. So what I'm going to do is I'm going to start by deleting all of the data points, and we're going to bring back just the ones that we think we want to provide extra weighting to. Initially, the first few months when we're flowing, we want to use that. I'm going to pick a few points just through the middle here. We know we have some productivity issues, so we're going to catch the high points and try and match the model just to the high points. I'm going to ignore all of this and just capture the region right around where we get our liquid level measurement, and then we'll catch some data at the end, and we'll try and make sure that that all of this matches. I'm going to put a little bit of weighting on some of these data points through here at the beginning, a few in the middle, and a few at the end. And this will hopefully ensure that we can bring that simulated pressure response down. Now for the automatic parameter estimation, we're going to use permeability, and we're going to use the XI, which is the stimulated region between the fractures. I'm going to put a maximum limitation on permeability to ensure that we don't go above 0.1 millidarcies. And we're going to do that on both K1 and K2. And we're ready to start the routine. So let's get this thing going. And our automatic parameter estimation now is trying to minimize the error between the simulated data set and the actual production. As you see this thing go, one thing you'll notice is that there's some divergence at the end between the simulated response and the actual data. And this is likely because our interpretation of the minimum volume is too small. So what we're going to do in this particular example, it just so happens that our minimum oil in place is very, very close to the well spacing that we have anyways, which is 320 acres. So I'm going to go ahead and just bump this up to 1395, which will bring us exactly to half section spacing, 320 acres. As you can see, this gives us a little bit more consistency in the late time. It doesn't make a great deal of difference, but it allows us to match the trend of that data at the end quite a bit better. And I'm just going to fine tune that one more time. Make sure we're matching it as best we can. Okay, and everything looks good there. And we'll just bring on the APE error. We're under 18%. That's a fairly good match of the data. So everything looks fine here. This is what I would call our best deterministic estimate or deterministic model based on the analysis that we've done. What I want to illustrate here, though, is that there are other models, other combinations of parameters that will give us history matches or may give us history matches that are just as good or better than this one. So there may be different combinations that are going to work just as well. So one of the things that I want to do is investigate what would happen if we assumed a different fracture half-length. What happens if the fracture half-length was much smaller? And this is one of the things that the analysis can't tell us, but the model will be able to illustrate this for us. So I'm going to auto-match around the same parameters that we were using before, but with a much smaller fracture half-length. And what we're going to find is that because the model is complex and has it has two different fracture regions, it has the ability to adjust the fracture, stimulated fracture width, we should be able to get combinations of parameters that give us just as good of a history match, but using completely different input parameters. Okay, so as we can see now, we have a very good history match. In fact, arguably better history match with a lower frac length. Although we're not going to use the logic that a better quality of history match in terms of the average error necessarily means a better model. We want to give all models that give us a good visual history match equal consideration in terms of the possibility that they could be the right model. So we want to provide a full accounting of all the different combinations of parameters that could work. So in doing so, let's do an investigation where we use a fracture length that is on the high end. And I think most people would argue that fracture length wouldn't exceed 500 feet effective fracture length. And so let's try doing a model match with 500 feet instead. And what we'll find is that we'll be able to get, through adjusting the other input parameters, we'll be able to get a match of the data using a high fracture half-length here as well. One of the things that you'd want to do in a real-life example as an operator is use the completion and stimulation data that you have at hand. So for instance, if very large fracture treatments are conducted per stage, you would want to favor your models towards higher frac lengths. In this and vice versa, if the completion size is much smaller, we want to favor smaller fracture sizes, and we can use that information to tune our models, or use fracture design modeling to tune our models. In this particular example, I'm leaving it wide open. I'm assuming that there's no information about fracture completion size, and we're going to just allow it to be open between 50 feet and 500 feet. Now, as you can see, we have a good match of the data here as well. We're at about 14% error. Visually, this is just as good as anything else. So what I've illustrated here is that there are 3 different analytical models with vastly different fracture lengths that all give us reasonably good history matches of the production data. Let's minimize that again. We can see a picture of what we have there. So now I'm going to go ahead and put the base model back in. It was 162 or 160 roughly feet. Let's maximize that again so we can see the history match. We'll bring back the original parameters and just get it to a middle line base model and settle back to that model. And we're going to do a production forecast for that model and look at what the long-term productivity and EUR will be for this particular example. All right, our next step is to do a production forecast. So we're going to make this 600 months, and we're going to forecast at constant pressure. Okay, you won't always forecast at constant pressure, but in this case, the final pressure in this production history is very low. It's very unlikely that we're going to get any lower than this, so it seems reasonable. Now we're looking at our EUR here. We have an EUR of about 500,000 barrels. I'm just going to launch another worksheet that will show this on a rate versus cumulative production plot. And we'll show our production forecast there. This equates to approximately a 10% recovery factor, so it's reasonable. One thing I want to talk a little bit about now, though, is this model has been done analytically. And because it's analytical, it will tend to be pessimistic in terms of fluid flow in the reservoir, purely for the reason that we assume that it's single-phase oil throughout the production history. In reality, there will be some solution gas that comes out either during the history or later on in the forecast that will provide some pressure support. So the physics of long-term production in these Bakken examples and other tight oil examples are going to be best approximated using a numerical model. So what I want to do is run a numerical model as well to validate and try and compare our interpretation with the analytical model. The advantage of the analytical model is that it's much faster. So we can run analytical models and their forecasts to get a good sense of what's going on and do sensitivities, but we need to run the numerical model to do a validation check. So let's launch a numerical model, and we're going to use black oil, gas plus water plus oil, and horizontal multifrac. Again, we're going to start by just seeding it with the existing parameters. And we'll just make that 1. Now when we do the history match with these input parameters, we're going to see some error between the simulated pressure response and the actual pressure response. Okay, the difference that we see between the simulated pressure response, and I'll just expand this so we can see it a little bit closer and move the gas and oil rates out of the way. The difference that we see between the simulated pressure response and the actual pressure response in the numerical is due to the fact that the analytical and numerical models make different assumptions. So what we need to do is we need to make some small corrections to the input parameters to get the best interpretation to get this data to match. And usually these are small adjustments that we make to permeability, sometimes to the fracture conductivity, and the stimulated fracture width EFR region to try and get that data to collapse down onto the actual pressure history data. Through trial and error, we've got some inputs here that work. We're going to make some changes here, and this will provide a much better match of the production. So we'll run that model again. And as we can see, the parameters with this model have generated a history match that is much better suited to the actual production pressure, the historical pressures of this data set. And we've done that by making some minor adjustments to permeability, fracture stimulated width, and FCD. We've left fracture half length exactly the same. Now the production forecast for this well is also of interest. So let's take a look at the forecast. We'll run that out also at a constant pressure for the same duration that we did for the analytical model. And what we're ultimately interested in taking a look at is the comparison between the analytical model performance and the numerical model performance. Okay, the numerical model forecast is complete, and we can see that the ultimate recoverable for this model is close to 1 million barrels, just under 1 million barrels. So what we're going to do is go over to the oil cum plot, and I'm just going to move that to the end. And we've got our analytical model on there that forecasts to about 500,000 barrels. And we're going to add the numerical model on top of there. And again, what this shows us is that there's a pretty significant range in terms of the long-term production forecast created by the analytical model, which makes the simple single-phase assumption, and the numerical model, which provides a much more optimistic long-term production forecast because it allows for solution gas to evolve. But let's talk a little bit about conceptually where we think the true solution would be. When we try to decide what is the best way to model, what is the best way to add realism to our production forecast going forward, we need to consider many factors, not just whether it's analytical or numerical, but all the other forecasting factors that come into play. There are so many uncertainties in these long-term production forecasts that neither model will necessarily be capable of handling. For example, forecasts from reservoir models always assume perfect operational efficiency, and this will rarely be the case in reality. So we have to worry about operational issues that may come into play. We have to worry about wellbore issues and surface issues that we're not necessarily including in either of these models. We also need to have the understanding that the true nature of the reservoir, if we go back to this numerical model, may be much more complex than what we have idealized here. In other words, this model is homogeneous in nature. There is a fractured region that has a different permeability than the reservoir region, but there may be other complexities in this reservoir that we're not accounting for. Just some of those complexities include regional variations in permeability and fracture conductivity, time-based and pressure-sensitive variations in well productivity over time, including effects that are in the fracture, such as fracture conductivity that varies with pressure and time, or reservoir permeability that varies with pressure and time. So these are all non-ideal situations that may cause the actual long-term forecast to be worse than what an ideal model would predict. So we think we actually have a pretty good range of possibilities here when we look at a numerical model and an analytical model. And what I'd like to do is come up with a way of making the analytical model look consistent with the numerical model. What can we do to the analytical model to make its long-term production forecast consistent with the numerical model? There's an advantage to doing that because the numerical model is much slower to run. It's not as practical to do probabilistic interpretation on. The analytical model gives us immediate feedback, gives us the answer right away. We can do automatic parameter estimation on it and get immediate feedback. So what we're going to do is try and get the analytical model to match the numerical model. And the way that we can do that is if we go back to our analytical model, we're going to adjust the total compressibility of the system. Remember, the component that makes the biggest difference in this long-term production forecast is the energy in the system. The energy in the system in the analytical model assumes that we have single-phase oil all the way through the life of this well. In reality, we're going to have some support from gas coming out of solution. We may also have additional support from formation compressibility. So what we're going to do, just as a starting point, is try changing this formation compressibility to something much higher. And I'm just going to estimate from a starting point that we have 2e to the minus 5, so 20 microsips. And this is just from trial and error. We've tried a bunch of different increases in energy, and this one seems to work fairly well. So what I'm going to do now is automatic parameter estimate around these, around permeability and XI again. And we should be able to get a pretty good match. We'll have to adjust permeability. Everything's going to have to be lower now because we've added more energy to the system. But as you can see, we can still get a fairly good match of the data. Our average error has actually come down significantly from what it was before. Okay, so we'll stop it there and take a look at our long-term production forecast. And now our EUR is up to just over 1 million. If we go back to the comparison of forecasts, what you can see now is that the forecasts are much more consistent with each other. The shape of the analytical forecast is a little bit different than that of the numerical, but they end up with very consistent EURs. So that is one way that we can translate the behavior of the analytical model to make it more consistent with the numerical model. That's not necessarily going to be a better forecast, but it's a way that we can make our analytical forecast consistent with the numerical model. We're going to use that concept later when we do our probabilistic interpretation. Before we get to that probabilistic interpretation, I'm just going to do a little bit of bookkeeping with my different analysis methods here, and I'm going to rename my analytical model. If I right-click on this one, I can provide a more descriptive name for it. So I'm going to call it analytical EFR. And this is the model that we're going to base our probabilistic interpretation on. And for the numerical model, we'll do the same thing. We're going to right-click, and I'll just call this numerical EFR. So the numerical is primarily for validation, or at least for comparison. So we now have our analytical and our numerical models in place. So I mentioned now we're going to go back to our analytical model, and I'm going to go back and change that CF back to what it was originally. And our default value for compressibility is based on the Hall correlation, and we'll rematch that again. So we're going to put our original parameters that we had in there before, and we're going to use that as a starting point for our probabilistic forecast. So why do we want to do probabilistic forecasting? Well, again, the reason is because we have so many different combinations of model input parameters, namely changing fracture length and permeability. Those are somewhat interchangeable, as we've learned. And so what we want to do is make sure that we're getting a range of different forecasts that are capturing the uncertainty in all of our input parameters to the best of our ability. So fracture length is one of them. The other one that is going to have some definite sensitivity on the forecast is that compressibility that we just looked at. So we're going to want to include that in there as well. So let's go ahead and create our probabilistic model. We do that by going to our risk and sensitivity analysis, and we'll create a new risk analysis. We're going to link that directly to our analytical EFR by clicking on that button. And so let's talk about this a little bit. We'll put some input parameters into our risk model that are going to be reflective of the uncertainty that we have. And I want to stress the importance of doing the sensitivity analysis on your analytical model prior to setting these things up. I think it's critical that we investigate, just by trial and error, the limits of that analytical model. And we did that earlier when we were investigating different fracture sizes and history matching around those different fracture sizes to get a sense for how those history matches were changing, and how we could get similar history matches with different combinations of parameters. So let's go through these one by one. Initial pressure I'm going to leave as a constant. For fracture half length, what we saw was that we had a range that was between 50 and 500. And I've purposely left this very open. The most open and unspecific way of stating an uncertainty range is to provide a uniform distribution. This says that there is no favorable region of fracture half length between 50 and 500. Anything can be randomly sampled between those two limits. I think it would be very difficult to argue that most fracture half lengths wouldn't be within that range. So I think that's a very reasonable and conservative way to state fracture half length. LE we're going to leave the same. Fracture conductivity we're going to allow to be an automatic parameter estimation. NF, that's the number of fractures. Let me talk a little bit about this one. For number of fractures, we have some different options. There is some way to provide a best estimate for number of fractures, particularly in the Bakken, where we tend to have open hole completions using sliding sleeve and ball drop for our fracture stimulations. So with these sorts of completions, provided that we can look at the operational reports and see that every fracture stage was successful and produced a fracture, we can normally assume that the number of fractures will be equal to the number of stages, in this case 35. However, we can provide some uncertainty along with that number if we like. And one way to do that is to use a triangular distribution, where we allow number of fractures to be less than 35 to account for the possibility that there may be fracture stages that are not contributing. On the other hand, if we have a plug-and-perf style completion, which is also used in the Bakken but is much more prevalent in other unconventional reservoirs, we can use a triangular distribution here where we apply a perforation efficiency or an efficiency factor to the total number of perforation clusters, make that the peak of the triangle, and then go plus or minus to do the lower and upper limits. So the way that we handle number of fractures is really dependent upon our knowledge of how the completion was created and how much confidence we believe we have in the number of fractures. In this particular instance, the completion report was looked at. Every stage was successful, so we're going to have pretty good confidence that we have 35 primary hydraulic fractures created as a result of this completion, and we'll leave that as a constant. For K1, we're going to change that to APE, K2, APE. These are going to be parameters that are calculated automatically in the model. Same with XI. This is typically going to be the case. We're going to allow the model to vary XF, and we're going to have it calculating the corresponding permeability and permeability region. For YE, we're going to leave that constant. That's based on the well spacing. We explored the model and found that it was very difficult to match with any volume less than about 1,300 or 1,400 feet. We found that the flowing material balance solution required, it was a little too small for a volume and required us to increase the volume. So 1395 represents the maximum possible volume based on the well spacing. There's really not a whole lot of room to put in a distribution there, so we're going to leave that as a fixed number. Now, for well properties, for well log properties such as net pay, porosity, and saturations, there's different ways to approach this, and it really depends on the log interpretation that you have and the petrophysicist's certainty or uncertainty around the parameters that have been estimated. It also depends on the region. In the Bakken, we tend to have pretty good confidence in some areas of the Bakken anyways, on what the log parameters are. The middle Bakken is a fairly thin formation. We can get pretty good confidence around H. In other plays, this may not be the case at all, so this is a very play-specific thing. But we can typically, what we do here is use triangular distributions. And triangular distributions are very useful if we have a best estimate, which is typically the mode, a minimum, and maximum range. So whenever we have a place where we can provide a best estimate and we have a minimum and a maximum, that is a good application for triangular distribution. In the case of fracture length, we used a uniform distribution because we did not have a best estimate. All we had was a minimum and maximum range. Here, for H, we do have the petrophysicist's best interpretation of H, which is 50. So I'm going to put that in for the mode. For the minimum, we're going to say there's very high certainty in this number, so we're not going to let it vary a whole lot. We're going to go plus or minus only a couple of percentage points. In fact, I think that's only a very small change on the upper and lower side. So there's our triangular distribution. We're going to do the same thing for porosity. So this one is going to be 7 in the mode, and it's going to be 6 for minimum, and it's going to be 8 for maximum. We're going to do the same thing for oil saturation. So again, this will be a triangular distribution. We're going to have 75 in the mode, and we're going to have 73 for minimum and 77 for maximum. For water saturation, we need to make that dependent because it depends on the value that we have for oil saturation. Now finally, let's take a look at the compressibility. We don't want to leave that as constant because we've investigated that there are possible solutions, namely the numerical model, where the average compressibility in the system could be much higher than the simple single-phase oil that's predicted by the analytical model. But we're not certain that that's going to be the best answer. That tends to be more towards the maximum solution. So what I'm going to do is I'm going to allow this to be a uniform distribution. And we're going to start this at a very low compressibility value consistent with the Hall correlation. And we're going to allow this to go to a maximum value based on the match with the numerical model, which was 2e to the minus 5. And this will give us a range of compressibilities that should capture, if we look at everything in between, and this is the value of doing probabilistic modeling, it should capture all the most likely forecasts or all the possible range of forecasts that will likely come out of the long-term production of this well. So this should give us the range. We've got our range of fracture parameters. We've got our range of CF. These will probably be the single two biggest influencers on long-term production. The uncertainty in log parameters will be very minimal, and then permeability and fracture region parameters are basically calculated parameters that will allow us to get the best history match on every run that we do. Now before we do this, we want to do a validation case. I'm going to reduce the number of runs that we do to 30. We always want to do a validation case before we run the full risk model, just to get a sense for what the results are going to look like. So this is a case that will give us a picture as to whether we need to make some changes or not before we commit to doing a full statistical set of runs, which will take much longer to do. And now before we go any further, let's look at our APE options. If I go back to my analytical model and look at the various different average errors that were in place, what we found was that everything was pretty much below 20% in terms of our average error. In fact, some matches had much better quality than others. So what we're going to do is we're going to say visually anything that is 20% error, this is close to it, this is 18%, or less is going to give us a good visual history match. Anything outside of that range we're not going to accept as a history match, and we're going to use those parameters in our risk model. So let me set that APE error to a maximum of 20%. We'll accept that, and now we're going to run the simulation. And when we run this simulation, again, this will give us some sort of validation case that we can run relatively quickly to get a sense of whether or not the risk model needs to be adjusted. Okay, so here's our results of our validation risk case. We have rate versus time, production shown here. We have rate versus cum shown over here. Let's just quickly go through what we're looking at. If I go ahead and, well, let's look at the rate versus cum plot first of all. What we can see is we have a couple of solid lines or curves. These are showing the P90, P50, and P10 forecasts. And then there's different color bands that represent different ranges of forecasts. The dark band in the middle is 1 standard deviation. The lighter band is 2 standard deviations, and etc. So this gives us a good sense for what the outputs look like. We're checking to see if the forecasts are reasonably consistent with the history, which they are. So this validation case makes sense. And the same thing with the rate versus time plots. Everything is making sense. It's consistent with the history. I think we're fine to go ahead and do the full risk analysis. If we look at the bottom two plots, these are frequency distribution plots or histograms that show us the statistical frequency that we get for EUR and for original oil in place. The more runs we include in our Monte Carlo simulation, the smoother these profiles will be. The reason that they're not very smooth and they look kind of noisy is because we've only done 30 runs in this particular case. So when we do the full set of statistical runs, hopefully we'll get a much smoother set of curves for both of these. So this is essentially validated in this case. Let's go back to our parameters. We're now going to set the number of runs to 300 instead of 30, and we're going to run this again. And this will take a little bit longer to run, but the results should give us a smooth set of statistical outputs. The probabilistic simulation is almost complete. As we can see, as we look at the number of successful runs, not all the runs are successful. And the reason that's the case is because we put that error limitation. So combinations of parameters that did not meet the history match error limitation that we prescribed are thrown out of the probabilistic interpretation. So this adds significant value to the process of exploring all of these different combinations of parameters, because we're only preserving the ones that would provide a level of history match that's consistent with what we expect. So let's take a look at the results. Again, we have our rate versus time plot shown here, rate versus cumulative production plot shown on the right hand side. These all look pretty good. They look consistent. So let's take a look at some of the histograms. Again, because we've run more cases than we did last time, we get a much smoother shaped bell curve. That's what we would expect to see when we run a statistically significant number of runs. There's always going to be a trade-off between number of runs that you're willing to commit resources to and the accuracy or statistical accuracy of the number of runs. Just simply by trial and error, we've found that if you have a number of successful runs that's higher than about 200 or 250, you're going to get a pretty smooth curve on most of these things. Again, on the original oil in place, again we can see there is a distribution. The distribution is fairly small range, mostly because we didn't vary the volumetric parameters in the oil in place significantly. We changed some of the log parameters a little bit, but not that much. The variance in ultimate recoverable is much greater because we have much more variance in our drive mechanism variables such as fracture length and compressibility of the system, and that's what causes the large range in EUR. There's other parameters output parameters that we can also take a look at, and I'll show those ones as well. So let's take a look at, for example, fracture length. Fracture length, we can see we have a pretty smooth variance, uniform variance between 50 and 500. However, you'll notice that there is a slight weighting to lower frac lengths rather than higher ones. The probability of seeing lower frac lengths comes out to be a little bit higher, and that's purely a result of the probabilistic run honoring the error tolerance that we provided. We didn't put that bias, we didn't build that bias into the inputs at all, so that came out purely as a result of doing that parameter space investigation. Let's take a look at some of the other results that we came up with. K2, this is permeability. This was entirely a calculated variable based on the XF as an input, and we find an overwhelming consistency. This would be a log normal distribution, so it's a left skewed distribution. Very few numbers come out extremely high, but we see a P50 in the range of about 2.5 e to the minus 3 millidarcies, and so most of the results are skewed towards the left, as would be expected when we're looking at permeability. There's a whole range of other inputs that we can take a look at if we're interested in things like FCD, which is our dimensionless fracture conductivity. We can also take a look at the XI variable, which is the width of the effective fracture region, and we can see a P50 of about 10 feet on that one. So these are all input parameters where we can get some confidence levels on what we think those are based on our probabilistic interpretation of the data. What we're really interested in here though are the forecasts. So what I'm going to do is go back to that oil cum plot, and we're going to start by just removing the existing forecasts that are on here. And what I want to do is overlay the analytical probabilistic forecast. So we have our P90, we have our P50, and we have our P10. And so we can get a sense for how much variance there is in these analytical forecasts. The P90 is coming in just higher than about 550,000, and the P10 is inching its way up to about 1 million barrels, with the P50 sitting pretty much in the middle. That's a pretty good result. That's consistent with the data. It makes sense. Reserve evaluators would probably accept that result. Everything looks fairly consistent. And we can add an element of ground truthing to this, again by overlaying the numerical model. The numerical model matches almost exactly the P10. Now what we want to point out here is that the EUR is almost 1 million barrels. The oil in place is close to 5 million barrels, so this is a pretty high recovery factor. So it makes sense that it would be this would be on the upper side of probability, so something closer to a P10 than a P50. And for our minimum case, let's use the deterministic analytical EFR model. That actually comes in lower than our probabilistic minimum case, and comes in at about 500,000 barrels. So we get a pretty good bracketed range here. We have our P50 in the middle, and this is the best approach for coming up with a long-term production forecast and the associated uncertainty based on modeling both analytically and numerically, and including all of the expected physics that we might see in that problem. And that completes the interpretation procedure for this Bakken example.